Welcome to day 11 of Just Start Programming, the Rust programming language. Yesterday we covered error handling, and for today we'll try to cover generic types, traits, and lifetimes. So let's go over once again quickly, just a quick review on what we have covered yesterday. So error handling, so for unrecoverable errors, I think there was uh, two ways of handling errors. One is recoverable and the other one unrecoverable. Two categories. And for recoverable, we use the result, while for unrecoverable, we had the panic macro. Okay, unrecoverable errors with panic. There was a way here in the cargo.toml where once it encounters panic, then it will just abort. So what is the implication? So yesterday we discovered that if we do this abort, then if we compile it as release, so there's a slight optimization in terms of code size, because that portion where Rust will handle the backtracking was um, was omitted. Yeah. So here, for example, this one, there's a vec macro where you can create a vector of signed integers, just like this. So this one will throw a panic, not unless if you handle it. And there's a configuration here for the environment variable, rust backtrace, then a number. So if you set rust backtrace equal to 1 and you do a cargo run, you will see like a stack trace on where the error occurred. So if you want the full backtrace, you can specify it like this in the environment variable. Debug symbols are enabled by default when using cargo build or cargo run without the dash release flag as we have here. In order to get backtraces with this information, debug symbols must be enabled. So by default, you get debug symbols. You do this. Yeah, without the release flag. So for release, again, there's some optimization that's being implemented. Okay, let's move on to the next one. Recoverable errors with result. So there's this result enum. It will take in two types, but you have to handle both OK and ERR. Yeah, so at first, Rust will show you the verbose way or the complicated way of handling errors. And then later on, in Rust, there's an alternative. So this one is already quite complex because there are multiple levels of match like this. And in cases where you have error like this and error like this, I think there was a question mark at the end. This one we don't understand yet. Why is it that there's a pipe here? Yeah, maybe in the future topics, upcoming topics, maybe we'll encounter this. Unwrap. So this is another way of handling it. If result is the error variant, unwrap will call the panic macro for us automatically. So if there's a panic, without specifying the panic macro, so it will be called automatically. And then here, so another way of handling it is expect in the display. Yeah, so these are the shortcuts. So it will return the file handle if it's successful. If it's not, then automatically call panic. So every time you see this line of code, unwrap and expect, eventually it will call the panic macro. So there's also a way to propagate errors. Error match return error. So you're returning error also. Yeah, here you're returning the error. And then there's that shortcut question mark. Rust provide the question mark operator to make this easier. So here, instead of going through complex implementation on how to handle it or propagating it, you can use the question mark operator. Yeah, so now you have a shorter code. Read to string, and then this one. So the question mark place after the result value is defined to work in almost the same way as the match expression we defined to handle result. So underneath, the equivalent code is how we handle the match. There's a difference between what the match expression does for and what the question mark operator does. Okay. Or you can even simplify it further. You can omit one of the variable definition by having just this one and then read to string. Of course, we need to use username, so we need to put it here. And if there's an error from here to here all the way up, it will be propagated to read username from file. Okay, so here you can do something like this directly. Read to string. Yeah, read to string. Creates a new string, contents of the file, puts contents in that string, returns it. So this one doesn't give us the opportunity to explain all the error handling, so we did it the longer way first. Yeah, of course you can do something like this. The question mark operator can only be used in functions whose return type is compatible. I think, yeah, somewhere here it mentions something about did it mention anything about generics? No. It did not mention anything about generics, unfortunately, or did I miss that? Okay, so one good thing about the question mark is you can do something like this. If the text is empty, string, this call to the next will return none. So this one will return none, and we wanted to handle that. So it will return some value. If not, then it will return result error. Or in this case, if it's some and none, so it will return none. Note that you can use question mark operator on a result in a function that returns result, and you can use the question mark operator on an option in a function that returns option. But you can't mix and match. The question mark operator won't automatically convert a result to an option. So far we've used return this one. Okay, so what that means is you can also return from main like this. And then there's this guideline when to use panic or not to panic. So we can revisit this later on as we do some actual implementation. We'll try to see how we can decide when to use panic or not to panic. Okay, let's move on. So today's session, I'm planning to learn about generic types, traits, and life types. So let's start with this. So every programming language has tools for effectively handling the duplication of concepts. In Rust, one such tool is generics. Abstract stand-ins for concrete types or other properties. We can express the behavior of generics or how they relate to other generics without knowing what will be in their place when compiling and running the code. Functions can take parameters of some generic type instead of a concrete type like i32 or string. In the same way, they take parameters with unknown values to run same code on multiple concrete values. In fact, we've already used generics in chapter 6 with option T. Yeah, so option type is a generic. Chapter 8 with vect and hash map. And in chapter 9 with result. So it's clear result is also generic. In this chapter, you'll explore how to define your own types, functions, and methods with generics. First, we'll review how to extract a function to reduce code duplication. We'll then use the same technique to make a generic function from two functions that differ only in the types of their parameters. We'll also explain how to use generic types in struct and enum definitions. Then you learn how to use traits to define behavior in a generic way. You can combine traits with generic types to constrain a generic type to accept only those types that have particular behavior, as opposed to just any type. Finally, we'll discuss lifetimes, a variety of generics that give the compiler information about how references relate to each other. Lifetimes allow us to give the compiler enough information about borrowed values so that it can ensure references will be valid in more situations than it could without our help. Okay. So generics, traits have something to do with how to define behavior in a generic way, and then lifetimes. So it's a variety of generics that give the compiler information about how references relate to each other. Okay, let's see. Removing duplication by extracting a function. Generics allows us to replace specific types with a placeholder that represents multiple types to remove code duplication. Before diving into generic syntax, let's first look at how to remove duplication in a way that doesn't involve generic types. By extracting a function that replaces specific values with placeholder that represents multiple values. Then we'll apply the same technique to extract a generic function. By looking at how to recognize duplicated code, you can extract into a function. You'll start to recognize duplicated code that can use generics. Okay. We'll begin with a short program in listing 10-1 that finds the largest number in a list. Okay, let's see. Main, then you have number list. So there's a vector macro wherein the vector can accept these values, and then a mutable largest variable referencing number list at index 0, so it starts from here. For number at number list, okay, number in number list, so it's borrowing it because this is a reference. If number is greater than largest, okay, so the first index is the largest. Largest equals number. Okay, so since largest is mutable, it can be changed. And number this is interesting. So can we assume that number is the copy value of the one in this one, in the first element? Number equals largest. So largest will now be 34. Number, wait. So if we start with this number list, so the first number is pointing to 34. So if number is greater than largest, which is 34, they're equal, this one will be skipped. But the next number is 50. So number is now 50. Number 50 is greater than 34. So 50 will be the largest. Okay. Then it goes on and on. So we store the list of integers in the number list, okay, and place a reference to the first number list in the variable largest, okay, reference to the first item in the list. We then iterate through all the numbers in the list, and if the current number is greater than the number stored in largest, we replace the reference in that variable. However, if the current number is less than or equal the next number list, after considering all numbers in the list, largest should refer to the largest number, which in this case is 100. Okay. We've now been tasked with finding the largest number in two different lists of numbers. To do so, we can choose to duplicate the code in 10.10-1 and use the same logic at two different places in the program. Yeah. So I can do something like this, and then you can do something like this. Oh, even the number, oh, everything is duplicated. Number list, so there's some shadowing being done here, and then mat also shadowing, and then yeah, number, okay. So basically it will run twice, having the same logic. Although the code works, duplicating code is tedious and error prone. You also have to remember to update code in multiple places when you want to change it. To eliminate this duplication, we'll create an abstraction by defining a function that operates on any list of integers passed in as parameter. This solution makes our code clearer and lets us express the concept of finding the largest number in a list abstractly. So we can create a function. Okay. We extract the code that finds the largest number into a function named largest. Then we call the function to find the largest number in two lists from 10-2. You'd use the function on any other list in i32 values you might have in the future. Okay, so we don't want to repeat the code. And then here, created a function named largest, where you have a list that references i32, and it will return a reference to i32. Okay, so it's almost the same. Item list, so list is this. Number list number list. List of I32. Okay. Number list is here. So largest you pass in the reference. Yeah, because this is a function. We are borrowing number list. Then result. Result returning a reference to I32, which is the largest. Let number list. Okay, it's used here again and returns result. Okay. The largest function has a parameter called list, which represents any concrete slice of I32 values you might pass into the function. As a result, when we call the function, the code runs on specific values that we pass in. In summary, here are the steps we took to change the code from 10-2 to 10-3. So we identified duplicate code. We extract the duplicate code into the body of a function, specify the inputs, and return values of the code in the function's signature. Update 2 instances of duplicated code to call the function instead. Next, we'll use the same steps with generic. So far what we have done here is just the basic way of avoid code duplication by creating a function. We haven't touched on generics yet. So we'll use the same steps with generics to reduce code duplication. In the same way that the function body can operate on abstract lists instead of specific values, generics allow code to operate on generics allow code to operate on abstract types. For example, say we had two functions, one that finds the largest item in a slice of I32 values, and one that finds the largest item in a slice of car values. Okay. How would we eliminate that duplication? Let's find out. Okay. So it's not just I32, but how do we eliminate duplication by considering car values also? Okay, so generic types. Let's see how long this is. Okay. Oh, it's quite long. We use generics to create definitions for items like function signatures or structs, which we can then use with many different concrete data types. Let's first look at how to define functions, structs, enums, and methods using generics. Then we'll discuss how generics affect code performance. In function definitions, when defining a function that uses generics, we place the generics in a signature of the function, where we would usually specify the data types of the parameters and return value. Doing so makes our code more flexible and provides more functionality to callers of our function while preventing code duplication. Continuing with our largest function, 10-4, this one. Two functions that both find the largest value in slice. We then combine these into a single function that uses generics. Okay, let's see. We have largest I32, largest car, I32, car, this, the same, largest, okay. The implementation here are the same. It's only the data type. Okay. So it means you can do something like this. The largest I32 function is the one we extracted in 10-3. Okay. And the largest car function finds the largest car in a slice. The function bodies have the same code, so let's examine the duplication by introducing a generic type parameter in a single function. To parameterize the types in a new single function, we need to name the type parameter, just as we do for the value parameters to a function. Can use any identifier as a type parameter name, but we'll use T, because by convention, type parameter names in Rust are short, often just one letter. And Rust type naming convention is camel case, short for type. T is the default choice of most Rust programmers. When we use a parameter in the body of the function, we have to declare the parameter name in the signature so the compiler knows what the name means. Similarly, when we use a type parameter name in a function signature, we have to declare the type parameter name before we use it. To define the generic largest function, we place the type name declarations inside angle brackets. Okay, angle brackets between the name of the function and the parameter list, like this. Okay. Declare the parameter name in the signature so the compiler knows what that name means. Similarly, when we use a type parameter name in a function signature, we have to declare the type parameter name before we use it. Okay. So here, largest, then, okay, so this is the type, generic. So it means that this T means this T and returns this T. We read the definition as the function largest is generic over some type T. Okay, generic over some type T. This function has one parameter named list, which is a slice of values of type T. Slice because of the square brackets. The largest function will return a reference to a value of the same type T. Listing 10-5 shows a combined largest function. Okay, so now it will look like this. So the implementation here is still the same. It returns largest. Okay, but now you have type T. Okay, because list here is known to have this type. And largest a reference to the type T. Okay, so here. Number list. So here it takes on I32. And here it takes car. Oh, but there's an error. If item greater than largest, restricting type parameter T with a type partial or. The help text mentions partial or, which is a trait. Okay, so now we encountered traits. And we're going to talk about traits in the next section. For now, know that this error states that the body of largest won't work for all possible types that T could be. Because we want to compare values of type T in the body, we can only use types whose value can be ordered. Okay. So only for ordered values. To enable comparisons, the standard library has the partial ORD trait that you can implement on types. See Appendix C for more of this trait. To fix the example code above, we would need to follow the help text suggestions and restrict the types valid for T to only those that implement partial ORD. The example would then compile because the standard library implements partial ORD on both I32 and car. Okay, so how do we fix? Let's try this out, and then do some experimentation. Cargo new B generics. Something like this. Will it compile? No, it already complained. Greater than cannot be applied to type %t. Okay, consider restricting type parameter t with a trait partial or. How do we do that? There's no quick fix. The example will then compile because the standard library implements partial ORD on both I32 and car. Okay. To enable comparisons, the standard library has so you can implement on types. We would need to follow the help text suggestions and restrict types valid for T to only those that implement partial ORD. Okay, let's see what was the recommendation. How do we restrict partial ORD? Quick fix. Okay. That's how you do it. So here we can use std compare partial ORD, and can remove this. Oops. There. Okay, now it will compile and run. Interesting. Okay. So restrict only to partial ORD. Partial order. Traits for types that form partial order. Okay. In struct definitions, you can also define structs to use a generic type parameter in one or more fields using this one, less than, greater than syntax. Okay, here it defines a point t to hold x and y coordinate values of any type x and y. Okay, so it can be I32, and then here this is what's this? I think this is like a float. I'm starting to forget things. Let's see. Data types. F. Yeah, so F should be F. Okay. The syntax for using generics in struct definition is similar to that used in function definitions. First, we declare the name of the type parameter inside angle brackets after the name of the struct. Then we use the generic type, the struct definition, where we would otherwise specify concrete data types. Okay, so the type is substituted here, it seems. Struct is a generic over some type T, and the fields X and Y are both that same type, whatever the type may be. If we create an instance of point T that has values of different types, our code will not compile. So that's not possible because it's T. But what if it's T, comma E, and this one is E? Or U? Interesting. Let's try that one. Okay, let me comment this out. Maybe move it up. Here. It out. So this is not allowed. Okay, so what if this is your STU? I'll put U. This is U. Is it allowed? Yes, it's allowed. It's allowed. F64, yeah. And if I use B, something like this, it work? Oh, this is. How do we put in binary? Ah, 0B. 0B. Okay. 0B. Oh, it's still I32. In table 3-2, note that the number zeros that can be multiple numeric types allow a type suffix such as. Okay. So it's still I32. Okay, so what I wanted to see is why is not this. We'll do a string colon from. Yeah, so it changes into string. Why would we change it to something else? So this could be arbitrary. So it can be V if I want. I don't know what is commonly used in Rust. But if I put T, then this is ambiguous. Yeah. So we need to. What if I put T2? Is that allowed? Oh, T2 is allowed. Covariant. Huh. Look at that. And it still works. I mean, the error is it's not being used, but here it's still string. T2. Okay. I explicitly put T1. T1. It will still work. But which one is the best practice? TU, T1, T2, or something else? Can it be number? Oh, we cannot use number. I32. Let's do something like this. Number I32. It's totally acceptable. Okay. But let's follow how Rust is doing it. Let's put it back and then string. And let's put 3 here. Okay. Okay, so we know that that won't work. Oh, it's using U. QRSTU, I was just guessing the next letter. Okay. So that will work. In enum definitions, as we did with structs, we can define enums to hold generic data types in their variants. Let's take another look at option T. Okay, so option T, as this is enum T. Yeah. And then for result, you have E. E, which represents error. E. Okay. Okay. And you recognize situations in your code with multiple struct or enum definitions that differ only in the types of the values they hold. You can avoid duplication by using generic types instead. In method definitions, you can implement methods on structs and enums. Yeah? So listing in point T, struct we define using 10-6 with a method named x. Okay, so let's see point, take in this type, implement point. Okay, point T is the struct, point 3 is the struct, implement T. This one, this is something new. Okay. And of course, self. And then here, okay, self, so that we can use x here. And then it will return a reference to the type T. Okay. Point px. Okay, so let's read what's the explanation for this. We have defined a method named x on point T, so it's referring to this. That returns a reference to the data in the field x. Note that we have to declare t just after impl, so we can use, okay, so you have to declare t. So we can use t to specify what we're implementing. Methods on type point t. By declaring t as generic type after impl, Rust can identify that the type in the angle brackets in point is a generic type rather than a concrete type. Okay. So this one will represent that t here is a generic type, not a concrete type. We could have chosen a different name for this generic parameter than the generic parameter declared in the struct definition, but using the same name is conventional. If you write a method with an impl that declares a generic type, that method will be defined on any instance of the type, no matter what concrete type ends up substituting for the generic type. Method with an impl declares a generic type. Okay, maybe there's some example here. Nope. This one looks different because impl here doesn't have the generic type. We can also specify constraints on generic types when defining methods on the type. We could, for example, implement methods only on point f. Okay, so only on point f32 instances rather than on point t instances with any generic type. Meaning we don't declare any types after, okay. So that's the purpose. Okay, so here, this is only if we are considering the generic type. So we can still implement a function with a specific type. Okay, whatever it is that it wants to do. Okay. This code means the type point f32 will have a distance from origin method. Other instances of point t where t is not of type f32 will not have this method defined. The method measures how far our point is from the method. Okay. That's the purpose of this. Generic type parameters in struct definition aren't always the same as those you use in that same struct method signatures. Okay. 10-11 uses the generic types x1 and y1. So that's right. You can do something like this for the point struct and x2, y2 for mix-up. Where's the mix-up? Okay. X2, y2 for the mix-up method signature to make the example clearer. Okay, here, mix-up. This is x2, y2, so this is different. Well, point x1, y1 is the generic. Self other point x2, y2. x1, y1, x1, y2. Why is it y2 here? This is a bit confusing. In the main, we have defined point that has I32. Okay, I32 for x with value 5 and an F64 for y. with a value 10 or 4. The P2 variable is a point struct that has a string slice. Okay, so it's string slice with a value hello and a car of y with value c. Calling mixup on P1 mixup. So P1 is point mixup P2. Mixup self other P2. Okay, so P2, okay. P2 is this one. This is P2. Okay. Gives us P3. With the argument P2 gives us P3. Okay. Which will have an I32 for X because X came from P1. Okay. Why will it have X of P1? X of P1. So mix-up is called and P2 is referenced here. No, it's not even referenced. It's borrowed. Okay. Then x2, y2 is actually hello and c. But it returns a point which is self x. X is coming from where? From here. Self x is hello. Then other, no. Self, okay, so now we have self and then other. The other is the second parameter. Self x of this one 5, other of this one c 5c. There will be okay, so here the P3 variable will have a car for y because y came from P2. Y came from P2. Okay, because of this other y, while other is P2. Yeah. So our analysis is correct. I think it's easier if we do a debug. I mean, if we print out some debugs. Okay. Let's put it here. So we know the answer, but we want to take a look what exactly is this. So we can put dbg macro. Okay, so these are the things that it's not added in the documentation, but it's our own way of investigating what exactly is going on here. Then to put in the bug, where shall I put the what's the term? What's the term? Doesn't implement debug. Okay. That was the I already forgot. Let's see. Where have we used it? CI method source main. Sharp derive debug. Okay. Can we put it here? Sharp derive and debug. Okay. Oh. Consider restricting the type parameter x1 with trait debug. How do we fix it? Why 2 doesn't implement debug? Into okay. Can we put something like this here? Can we do something like that? No. Structs, enums, and unions not applicable. Okay. So it should be there in the struct. Not. How do we fix this one? Self. Okay, so we cannot do it like this. So if you cannot do it like that, then mix up. Maybe we can do something like this. Of course, it's DBG. Can only do it from here. Oh, it shows point x colon 5 by c. Yep. This is good enough. Yep. Okay, so let's move on. I think this is the explanation. We covered that. Only relevant to the method. Okay, performance of code using generics. You might be wondering whether there is a runtime cost when using generic type parameters. The good news is that using generic types won't make your program run any slower. Nice. Than it would with concrete types. Rust accomplishes this by performing monomorphization. Oh, this is something new. I've heard of polymorphism. I don't know if that's correct. This one has performing monomorphization. Okay, let's read on. Of the code using generics at compile time. Monomorphization is a process of turning generic code into specific code by filling in the concrete types that are used when compiled. Okay. Process of turning generic code into specific code by filling in concrete types that are used when compiled. Filling in concrete types that are used when compiled. In this process, the compiler does the opposite of the steps we use to create a generic function. Compiler looks at all the places where generic code is called and generates code for the concrete types the generic code is called with. So does it mean that I think compilation will take some time if it has to do something like this? Let's look at how this works by using the standard library's generic option t. Okay. Let integer sum5 float sum 5.0. Okay, sum is from option. When Rust compiles its code, it performs monomorphization. During that process, the compiler reads the values that have been used in option t instances and identifies two kinds of option t. One is I32 and other is F64. As such, it expands the generic definition of option t into two definitions specialized to I32 and F64, thereby replacing the generic definition with the specific ones. The monomorphized version of the code looks similar to the following. The compiler uses different names than what we're using here for illustration. So it converts option into option I32 and F64. To our convenience, we can do something like this, but behind the scenes, the compiler will create something like this. Okay, generic option is replaced with the specific definitions created by the compiler because Rust compiles generic code into code that specifies the type in each instances. We pay no runtime cost for using generics. Rust compiles generic code into code that specifies the type in each instance. When the code runs, it performs just as it would if we had duplicated each definition by hand. The process of monomorphization makes Rust generics extremely efficient at runtime. This is something to think about, how we use generics. Okay, so maybe let's copy this and take a look how it appears in Visual Studio Code. Maybe it can give us some more clues. So option I32, F64. Quick fix unused variable. Okay. So here we can just see that it's an option with F64. It would be also interesting if we create so many of these different types and see how it will affect the code. Yeah, we can probably do that experimentation some other time. Yeah. Okay, let's move on to traits. Traits defining shared behavior. A trait defines the functionality of a particular type, has and can share with other types. We can use traits to define shared behavior in an abstract way. We can use trait bounds to specify that a generic type can be any type that has certain behavior. Note, traits are similar to a feature often called interfaces in other languages, although with some differences. Okay. Traits like interfaces. Okay. Defining a trait. A type's behavior consists of the methods we can call on a type. Different types share the same behavior. If we can call the same methods on all of those types. Trait definitions are a way to group, trait definitions are a way to group method signatures together to define a set of behaviors necessary to accomplish the same purpose. Okay. For example, let's say we have multiple structs that hold various kinds of amounts of text. A news article struct that holds a news story filled in a particular location, and a social post that can have at most 280 characters along with metadata. Indicates whether it was a new post, a repost, or a reply to another post. We want to make a media aggregator library, trait name aggregator, that can display summaries of data that might be stored in news article, social post instance. To do this, we need a summary from each type, and we'll request a summary by calling summarize method on an instance. Listing 10-12 shows the definition of a public summary trait that expresses this behavior. So now we have trait, summary, and then the function summarize is a self-turning string. Okay, so here we declare the trait using trait keyword, and then the trait's name, which is summary. In this case, we also declare the trait as pub, so it can be called. So that traits depending on this trait can make use of this trait too. We'll see in a few examples. Inside the curly brackets, we declare the method signatures that describe the behaviors of the types that implements this trait, which in this case is fn, summarize, self, string. So you see there's no implementation, but it shows you that you have a method name summarize, the self parameter, and it will return a string, but there's no implementation. So this is like exactly how interfaces are in other languages. Okay. After the method signature, instead of providing an implementation with curly brackets, we use semicolon. Each type implementing this trait must provide its own custom behavior for the body of this method. The compiler will enforce that any type that has the summary trait will have the method summarize defined with this signature exactly. A trait can have multiple methods in its body. The method signatures are listed one per line, and each line ends in a semicolon. Okay, so I think before we proceed further, let me just save this one, close this, and reserve another project for traits, and code dot. Okay. Let's try something. So this is summary. Okay. Pub trait summary. Can we copy this one? Put it here. So do something like struct. What's that? News article. News article. Then how do we implement news article function that summarize self remove this, then it will return string. So this one string from, can we do something like this? News article summarize. Not message equals oh. Just type it in. Okay, what I'm trying to do here, how to return string. Can we do something like this? String. Oh, like this. Okay. Message. Summarize. But how do we make use of trade summary? Can it be like summary like this? I don't know. Maybe. Let's see how it will look like later on. And no news article will implement summarize, but it will have the same signature but different behavior. Okay, let's prepare that for now. implementing a trait on a type. Oh, it's here. Okay. Implement summary for news article. Oh, okay. Implement summary for news article. Because struct is here. Implement summary for news article. So that's how you do it. Implement summary for news article. So I wonder if okay, let's make this pub. It's not necessary. I can have this pub as well. I think it's pub function. Oh, it's wrong. Visibility qualifiers are not required. Okay, what will happen if I'll comment this out? Yeah, summary will complain that you need to implement summarize. Implements the missing. Not all trait items implemented. Yeah. And then the quick fix will, boom, do something like this. So it's almost similar with other programming languages. Okay, we can remove this. Then uncomment this. Okay, that is clear. So you can implement something like this. News article with headline, location, author, content, and here summary. Okay, implement summary for news article. This headline, author, location. While if you have social post, you can implement summary for social post. Summarize will have the same signature but different behavior. Okay, so let's copy this. Then let's change this one. Put it here. There. So here, if you do a social post, equals to social post we have username, username, what shall we put? Is this correct? So wondering if this is correct. Bob. So there are other things missing. Bob, comma. What What's the other one? Content. Content ABC. Reply. ABC. ABC. Okay, then the other one, repost. True. Oh, not semicolon. Okay, what's the issue here? That string, so string colon from. It's also a string colon from. Okay. This is bool. Okay. Boolean. So reply false. Okay. And then let's copy this. And here. The other one, news article. Okay, social post, news article. And here, change it to news article. There we have author string from William Faulkner. This is their content. Content is content. Okay, content is string from 1, 2, 3. Yeah, set line. Breaking news. This is here location. String from okay. And social post dot summarize the above. Let me do something like this. Use article summarize. Okay, let's see. Social post summarize above content ABC. News article summarize breaking news by William Faulkner Island. So although we are calling the same function, it has different behavior. And we just define the trait summary. Oh, can we have multiple traits? Is that possible? Say summary for news article. Or can we have I don't know, maybe let's see. Can we have multiple traits? Let's experiment. Trait what can we do? Okay, maybe very verified. Oh no. Authenticity, something like that. And here instead of summarize, verified. Yeah. Let's see. Can we put something here like a comma? Authenticity. Okay, there's an error. No quick fixes. So we cannot use comma. Colon. I'm just guessing. No, maybe we'll see. We will see in we'll see some examples here. Okay, let's see. Summary trait. I think we've done that. Content. Okay, we've done this. Other traits that depend on aggregator trait also bring summary. Okay. See. We can't implement external traits on. Oh, what is this? Other traits that depend on the aggregator trait can also bring summary trait into scope, their own types. One restriction to note is that we can implement a trait on a type only if either the trait and the type or both are local to our trait. For example, we can implement standard library traits like display on a custom type like social post as part of our aggregator trait functionality because the type social post is local to our aggregator trait. We can also implement summary on vect in our aggregator trait. Because the trait summary is local to our aggregator trait, but we can't implement external traits on external types. For example, we can't implement the display trait on vect within our aggregator because display and vect are both defined in the standard library and aren't local to our trait. So I think it has something to do with the scope. This restriction is part of a property called coherence, and more specifically, an orphan rule. So name because the parent type is not present. This rule ensures that other people's code can't break your code, and vice versa. Okay. Without the rule, two traits could implement the same trait for the same type. and Rust wouldn't know which implementation to use. Yeah, so it will become ambiguous. Ambiguous. Yeah, so I should avoid two crates could implement the same trait for the same type. Default implementation. Sometimes it's useful to have default behavior for some of all of the methods in the trait instead of requiring implementations for all methods of every type. Then, as we implement the trait on a particular type, we can keep or override each method's default behavior. We specify a default string for the summarize method of the summary trait instead of only defining the method signature. Okay, summarize string from read more. Okay. To use a default implementation to summarize instances of news article, we specify an empty IMPL block with IMPL summary for news article. Empty IMPL block. Even though we're no longer defining the summarize method on news article directly, we've provided a default implementation and specified that news article implements the summary trait. As a result, we can still call summarize method on an instance of news article. How is that possible? Yeah, I think it's not here, but it's something we can implement. Article summarize. Okay, and here this becomes as a default implementation. Okay, implement. Okay, can we comment this out and then news article we can something like this. Can still compile, but in this case, this article will display read more. Let's see. Yeah, read more. Okay, but what if we implement summarize? Implement summarize. Oh, there's no error. No error. So does it mean this one will override this one for news article? Let's see. That would be interesting. Breaking news. Correct. So that's how it is. So just like in interfaces, I guess. Or I'm not sure. Somehow this approach looks familiar. So although we define a trait and we wanted it to have this function signature, but in cases where it's not implemented, you're not bound to implement it here in news article. Let's mean news article, since the implementation is already here. So it's quite convenient also. And you have a default behavior. Okay. Okay, default implementation can call other methods in the same trait, even if those other methods don't have a default implementation. In this way, a trait can provide a lot of useful functionality and only require implementers to specify a small part of it. For example, we could define the summary trait to have a summarize author method. This implementation is required. Yeah, because there's no default implementation here. Now the summarize method has has a default implementation called summarize author. Oh. What will happen if this is not implemented? Okay, to use this version summary, you only need to define summarize author. Okay. Anyway, at compile time, social post, yeah, 8. Summarize author. Yeah, social post is required to implement summarize author. Then summarize author would be fine because anyway, social posts have implemented summarize author. Okay. Oh, what is this? Format. This is something new. Self username. Social post summarize. Okay. Summarize will still be called code prints. Read more from author's ebooks. Oh, this one nothing special. Yeah, so it's just to show this string. Okay. Note that it isn't possible to call the default implementation from an overriding implementation of the same method. Overriding method. It isn't possible to call the default implementation from an overriding implementation of that same method. Let's see if there's some example here. Okay, maybe at compile time this one will throw an error. Okay, let's move on. Traits as parameters. Now that you know how to define and implement traits, we can explore how to use traits to define functions that accepts many different types. We use summary trait we implemented on the news article and social post. We define and notify. Okay, so this is a new one. Some implements the summary trait. To do this, we use the IMPL trait syntax like this. Okay. To define a notify function that calls summarize method on its item parameter. Okay. So if you have a function notify, then you have an item parameter. You want it to be able to implement summarize, then you need to have at IMPL summary. Okay. Now this is a bit complex. This is so that you can call summarize from summary. Traits as parameters. Okay, I mean that's the purpose. Traits as parameters. Item summarize. So it's like summarize doesn't require any variables that needs to be manipulated inside based on the object. I think it's like a static function. or I might be wrong. But as of now, that's how I see it. Instead of a concrete type for the item parameter, we specify MPL keyword and the trait name. This parameter accepts any type. Okay, it can accept any type that implements the specified trait. The body of notify. We can call any methods on item that come from the summary trait, such as summarize. Can call notify and pass any instance of news article. Okay, we can call notify and pass in any instance of a news article or okay, so yeah, so any struct that implements summary. So since they implement summarize, so that function will be called. That's interesting. So I was wrong. I was wrong earlier about static function. Code that calls a function with any type such as string or I32 won't compile because those types don't implement summary. Trait bound syntax. The MPL trait syntax works for straightforward classes, but is actually syntax sugar for a longer form known as trait bound. It looks like this. Trait bound syntax. Okay. Notify. Okay, so type summary item at T. Is it the same as this one? Ultimately, the result here are the same, but you're putting it here. Trait bound syntax. Item. So at T, so this could be news article. Yeah, so the T will T having the summary trait, so that from T you can, from this item, we can call the function from that trait. This longer form is equivalent to the example in the previous section, but is more verbose. We place trait bounds with the declaration of the generic type parameter after a colon and inside angle brackets. The IMPL trait syntax is convenient and makes for more concise code in simple cases, while the fuller trait bound syntax can express more complexity in other cases. For example, we can have two parameters that implement summary. Two parameters that you can implement item 1, item 2. Yeah, summary, okay. Doing so with the IMPL trait syntax looks like this. Yeah, this is IMPL trait syntax. Using IMPL trait is appropriate if you want this function to allow item 1, item 2 to have different types. Yeah. So if this one will have different types, then this way makes sense. However, if you want to force both parameters to have the same type, you must use a trait bound like this. Okay, so item, okay. So that's the benefit of doing it like this. The generic type T is specified as the type of the item 1 and item 2 parameters constrains the function such that concrete type of the value passed as an argument for item 1 and item 2 must be the same. Specifying multiple trait bounds with a plus syntax. You can also specify more than one trait bound. Say we wanted notify to use display formatting as well as summarize on item. We specify notifying definition that item must implement both display and summary. You can also do so using the plus syntax. So with item alone, you can implement both summary and display with the plus. Okay, so this is at function, okay, function level. Okay. Plus syntax is also valid with trait bounds on generic types. Notify. So you can do it like this also. With a two trait bound specify, the body of notify can call summarize in the use of is to format item. So, okay, implement summary. That is for the trait and as to how the trait will be used. Oh no, the function. Yeah, but okay, you have a function that will take in traits. Okay, so I think if that's how it is in Rust, then I was looking for answers where summarize and then there's another function implementation here for a different trait like verify. Okay, so we didn't have that answer yet. But by a function itself calling the traits of this, okay, these traits, different traits, is possible. Okay. Clearer trait bounds with where clauses. Okay, so now we're still at functions. Display plus clone, okay, that is for type T, while for type U, clone plus debug. Then T, okay, this is the type, and then U. This is beginning to be more complex. Where a where clause can be used like this. We can use where clause like this. Okay. This function signature is less cluttered. The function name, parameter list, and the return type are close together. Similar to a function without lots of trait bounds. Okay, so you have an option to use where clause. These functions in, okay, less cluttered. Returning types that implements traits. Okay. Yep, so I think we can end here and do a recap following day. Yeah, so because these things here, we need to clearly understand what it means. So let's continue tomorrow. Save it for another day, tomorrow or the following day. Once again, thank you so much for accompanying me throughout this journey while I'm studying a Rust programming language from scratch. So I don't know how Rust works. That's why I'm reading through the documentation, doing some experimentation. And by doing it together with me, hopefully you can gain some insights as well. Yeah. Thanks once again. Goodbye for now.